Hello everyone, I am Deepak Paliwal. So in the continuation of the previous lecture, so today we will discuss about the sleep systems in case of FCC. Okay, so for as we have seen in the BCC for sleep system calculations, sleep systems in FCC. So as in the case of BCC, we use planar density and planar and let me erase it and linear density to find closed pegged plane and closed pegged direction. So in case of FCC also we will do the same thing. We will find out the closed peg plane and closed peg direction. Those plane which has uh, largest planar density and largest linear density, that will become the part of our sleep system. As I have mentioned previously, the sleep system comprises of uh, a closed peg plane and a closed peg direction. So now let's find out what is the closed peg plane and what is the closed peg direction in case of FCC. So here first let me draw FCC unit cell. Similarly, what we have done in the BCC, we will calculate the planar densities for 100, 110 and 111 plane. Let me draw the atoms here. So these all are the corner atoms. Let me draw with some different colors the FCC atoms. As we have in cube 6 faces, so we have 6 atoms here. Okay, so we have marked all 6 atoms here and all 8 corner atoms. So now what we will do, we will do calculate for 100 plane, 110 plane and 111 plane. So planar density we know is equal to number of atom in a plane, area of a plane. So let me show you what is the this 100 plane. So the 110 plane is 100 plane belongs to this, which I highlighted with the help of yellow color. Let me take this out for the simplicity to understand. This is our 100 plane which has corner atom. Okay, additionally it has face centered atom. Okay, so now the total number of total number of atoms in 100 plane is equal to 4 atoms. Each atom is contributing to the 1 by 4 to this plane and one face centered atom. So total number of atom becomes 2. Now area, this is A, this is A. What exactly we have done there? So the area of 100 plane is A square. So planar density of 100 plane is equal to 2 by A square. Now we will calculate for 100 plane. So let me draw the 110 plane. This is 110 plane here. Let me hatch it for the simplicity. I will take this plane out from this unit cell also. So let me take this plane again. I am mentioned in the previously also, one side of this plane we need to show larger, and we have atom here, atoms here, atom here. We have additional atoms at this position. So these atoms, let me mark with different color. This is the atom, this is the atom. So you can see this is the atom and this is the atom, and at the body center we do not have atom, and at this uh, center of this edges we do not have atom. So similar thing, we have taken it out from the cell and we know the distance, this distance is root 2a. Again I will I am mentioning this distance is root 2a and this distance is a. So I will write it root 2a and this is a. So total number of atoms in 110 plane is equal to 1 by 4 into 4 plus 1 by 2 into 2, because this atom is contributing to 1 by 2 to this plane. Okay, so we have one here, so the total number of atom is again 2. So this is 2 divided by area is root 2a multiply with this side, so the area becomes root 2a square. Okay, so we have planar density for 110 plane is root 2 a square. Okay, now we will calculate the planar density for 111 plane. I am calculating here, or I will move to the next slide here. Now we will find out the planar density for the 111 plane. So let me show you what is the 111 plane, maybe with some different color. Okay, this is your 111 plane. Let me hatch it down. So this is our 111 plane. Let us calculate 111 plane planar density here. So we have a triangle. Okay, so we have corner atoms. Okay, let me draw with different colors. This face centered atom, this is our one face centered atom, another face centered atom, this is another face centered atom. Okay, so let me first calculate total number of atoms here is equal to 1 by 6th contribution of each corner atom, and we have 3 plus 1 by 2 contribution of each atom of each face centered atom, and it is contributing 1 by 2 contribution of each face centered atom, and it is 3 in number. Okay, so this is 1 by 2, this is 3 by 2, so this is 4 by 2. So there will be 2 number of atoms. And what we have calculated area of a equilateral triangle in case of when we were calculating the one planar density of 111 plane in case of BCC. So we have calculated the area of this equilateral triangle, which was come out to be, so that area comes out to be root 3 by 2 a square. So we will calculate the planar density here, maybe with different color. Planar density, number of atoms in a plane, that was 2. Area of the plane, this is the area, so root 3 by 2 a square. Reason behind I am doing all this exercise on this page, so that we can compare the results here. So root 3 by 2 a square. So finally planar density for 111 plane comes out to be, let me write, 4 by root 3 a square. So now we can see here the planar density for 100 is 2 by a square, planar density for 110 is root 2 by a square, and planar density for 111 plane is this much. So the maximum planar density for uh, FCC FCC plane is or the maximum planar density, or the closed packed plane, or the closest packed plane in case of FCC is 111. So this is the maximum. Okay, so if I write it like this, planar density of 111 plane greater than planar density of 100, then the planar density of 110. So the closest packed plane is 111. Now we will discuss about the closed peg direction in case of FCC. Let us firstly draw a unit cell. As usual, we are drawing the unit cell, our FCC unit cell. Okay, this is our corner atoms. Let me mark with different color the FCC atoms. Back face, this is the front face. Okay, now what is the linear density? As we have seen in the previous lecture, linear density is equal to number of atoms on the line divided by length of the line. Okay, so as we have seen previously, we will calculate for 100 direction, 110 direction, and 111 direction. In case of 100 direction, what is our 100 direction? So this is our 100 direction. These all are one family of 100 direction, belongs to the family of 100 direction. Whatever I am drawing here, these all are 100 direction or family of 100 direction. So I am taking out 100 direction here. Is this is the 100 direction. So we have one atom at the two atom at the corner of this length, and total number of atom is equal to what? Is equal to, we have two atoms, each is contributing to each is contributing 1 by 2. So we have only one atom in this length, and the length of the line L is equal to A only. So linear density for 100 direction is equal to 1 number of atom divided by length of the line. Again we will calculate for 110 plane. So 110 direction, sorry for I said plane. So we will calculate the linear density for 110 direction. So let me show what is the 100 direction. So this is our 100 direction. So let me take this out here. This is our 100 direction. Look here, I have what I have shown here. Okay, actually these atoms now touching each other. Just for the simplicity I am showing these are not touching, but these atoms are touching each other. So I am talking about this one, these atoms are touching each other. So now this is the 110 direction. Okay, so the length of this direction would be, this is A. Okay, this is A, this is A. So this will be root 2A. So the length of this line is root 2A. So the total number of atom is equal to 1 by 2 is the contribution of each atom at the corner of the line or this direction, which is contributing 1 by 2. There are two atoms and there is one face centered atom, so there will be two atoms, and length of the line is equal to root 2a. Now linear density is equal to 110 is equal to number of atom and length of the line, so there will be root 2 by a. Now we will calculate for the 111 direction. So let me find out my 111 direction. So this is my 111 direction. Okay, which is I am pointing out here, this is 111 direction. So we will have 1 direction. So the atoms at the 111 direction will be this one and this one. Okay, so the length of this line, like this is the root 2a, this is a, so this will be root 3a. Okay, so the length of this line is root 3a. So the total number of atom is equal to 1 by 2 into 2 is equal to 1. Length of the line root 3a. Now linear density for 111 direction is equal to number of atom divided by root 3a, which is the length of the line. Now see, this is the linear density for 100, this is the linear density for 110, and this is the linear density for 111 direction. Now if we observe, then what we'll find, the maximum density for 110, and the order goes like this: linear density for 110 is larger as compared to uh, your linear density of 100, then linear density of 111. Okay, so the closed peg plane in case of FCC, and closed peg plane is our 111 plane, and closed peg direction is 110 direction. Okay, so in case of BCC, this is for FCC. In case of BCC, closed peg plane was your 110, and the closed peg direction was 111, which is just opposite in the case of FCC. So we have seen some basic information about the simple cubic, about BCC, about FCC. We have calculated the closed peg plane and closed peg direction for the BCC and FCC. So in the next lecture we will talk about the what are the how many number of the sleep system present in case of FCC. Now onwards we will more focus on the FCC. We will not discuss about the BCC. We will our main focus on the deformation mechanisms of FCC. So we will try to understand what are the sleep systems and how many number of the sleep system in case of FCC. For the so for till the next lecture, bye bye, and thank you for listening this video. Okay.